What's up, everybody? In this video, we're going to learn how to do USACO 2021 February contest at the bronze level. Problem number 3, clockwise fence. Let's read it together. The fence surrounding Farmer John's largest pasture has fallen into disrepair, and he has finally decided to replace it with a new fence. Okay, so he's got a pasture, he's got some sort of a fence around it. Unfortunately, as Farmer John is laying out the new fence, a large bee ends up chasing him around the pasture as a result. As a result, the fence ends up following a rather irregular path. The fence can be described by a string of characters, either with N for north, E for east, S for south, or W for west. Okay, so we're describing a fence that's going to be kind of wacky by northeast, southwest directions. Each character describes a 1 meter run of fence. For example, if the string is NESW, then that means the fence starts by moving north for 1 meter. Okay, so from here we go north, and then east for 1 meter, east, then south for 1 meter, south, and then west for 1 meter, west, and that makes the fence. Returning to its starting point. So we can rely on the fact the fence is going to be a complete fence and should end where it started. The fence ends at the position where it started, and this is the only point visited more than once by the path of the fence. Okay, good. So that means the fence can't cross itself. We have to have an irregular fence that encloses a space but doesn't do a crossover or make any separate pockets. There's only going to be one enclosed area. As a result, the fence does indeed include a single connected region of the grassy pasture, even though this region could have a rather strange shape. Farmer John is curious if the path in which he laid the fence traveled clockwise with the enclosed region on the right side of the fence as one walks along the path of the fence in the order specified by the string, or counterclockwise with the enclosed region on the left side of the fence. Okay, so for example, in this particular fence that we just did, we went north and then east and then south and then west. As he's walking along, the enclosure would have been to his right side and the open space would have been to his left side. So since the open space is to the left and the entire time he walked around, the open space is to his left and to his right was the inside, that means that this is the direction he walked in, which is clockwise. So they're describing clockwise, which means the enclosed region is on the right side. Versus, for example, counterclockwise, which would mean the enclosed region would be on the left, which would mean he would be traveling the other way, and that would be counterclockwise. Okay. Scrolling down to input. Input format comes from the terminal and standard inputs. This is just typed into the console. The first line of input contains an integer of n, where n is 1 through 20. Each of the next n lines, so this is how many test cases you have. You have up to 20 test cases. Each of the next n lines contains a string of the length at least 4 and at most 100. Okay, so at most these fences are going to be 100 characters long, but they will be at least 4 because you need at least 4 in order to close your path. The output format is just printed to the console, so you can just print or output or see out or whatever. For each of the n fence paths described in the input, output a line containing either CW for clockwise or CCW for counterclockwise. All right, so let's look at these two fence examples. So I got 2 examples. Here's the first one. First one, we went north, we went east, we went south, and we went west. That clearly was clockwise. So the first output is clockwise. Let's look at this next one. This looks a little more complicated. So we went first west and south 3 times. South, south. East twice. East, east. North once. West once. North once. East twice. South twice. East once, north 4 times, west 3 times, 1, 2, 3, and then south once, arriving in this path right here with the enclosed area being to the left and the open area being to the right. And they described that when the enclosed area, here it is. With the enclosed area on the left, as we just said, this is the enclosed area on the left, that defines counterclockwise. which is CCW. And if you just kind of eyeball that, it does seem like he's generally going in a counterclockwise direction. All right, so in order to be able to solve this, and look, they drew these out for us. Yeah, here's the one I just drew. Okay, so in order to be able to solve these, the way you're going to approach these kinds of problems is by drawing out as many examples of this as you can think of. Just do one after the other. Try to think about what kind of patterns we're noticing as far as what is a clockwise versus what is a counterclockwise fence. For example, if I'm traveling this way and I start to go this way, it looks like I'm going to be going this way, which is counterclockwise. But then if I suddenly change and go this way and up over and down, now it's starting to look like this actually is going to be a counterclockwise fence. But then again, I can change direction. Over, you get the idea. Going down here. Now this is starting to get a little confusing, but if I were to then go back and enclose this, then I'm arriving like this. My enclosed area is to my right side here, which means that ultimately, if you look at this path that I followed, it's mostly clockwise. Okay, so how do we know that this is clockwise? What is it that's determining? Because it seems like we can change it by turning and going the other way. So let's kind of redraw this one example again and think about what happened. When I was starting off, think about which way I turned. If I'm doing a clockwise, I'm going to be turning right. And if I finished that, that would have been a right turn, a right turn, and a right turn. I would have had all right turns, pretty much no left turns. And if it's all right turns and no left turns, I've got clockwise. Let's see what happens if I mix it up though. If I go up here and then I turn right, that's a right turn. If I turn right again, that's another right turn. But here now I'm going to turn left. That becomes a left turn. And this again is a left turn. Here I'm going straight. Here's a left turn. Going straight again. Going straight again. Another left turn. And then if I were to turn left one more time and close that, then I would have a total of 5 left turns and 2 right turns. So let's back this up a minute. The first one we looked at, all the way back here, if I would have turned right another time, then that would have been 3 right turns total, which would have made a clockwise fence. So that's 3 right turns to be clockwise. I'm gonna write that down here in a sec. Right turn. If right is 3 and left is 0, that's gonna be clockwise. CW. That's what direction we're in. Actually, I'm gonna move that down a bit. A little kind of mashed over there. Okay. If my right was 3 turns and my left was 0 turns, then my direction in that case would have been clockwise. Likewise, if I would have had 0 left turns and 3 right turns, that would have been counterclockwise. This that I've done here, I have 2 right turns and 5 left turns, which was ultimately counterclockwise. And likewise in reverse, if I had 5 and 2, then that would have been clockwise. So what started out, what was almost going to be 3 right turns, which would have been clockwise, became 2 right turns and 5 left turns, which was counterclockwise. Let's try to actually, let me just focus on these examples here, the clockwise versus counterclockwise. I think that'll be simpler. 2, 5, CCW. And just bear in mind that if you invert these numbers and it was 3 left and 0 right, for example, then that would just be the opposite. Same if it was going to be 5 right and 2 left, then that would be clockwise instead of counterclockwise. But if I were to cancel this last left turn, and my left turns total now drop down to 4, and then I go right turn again, then up, and then here a right turn, then and then to here, and another right turn, all the way down here. This will have to be another right turn, all the way to here, and another right turn. All right, and then that would close that off. So let's see how many rights and lefts I have. I now have 4 lefts. Let me write that up a little higher. I have 4 left turns. I have, let's count them, 1, 2, 3, 4, 5, 6, 7, 8 right turns. And then this one, we feel like this, I think, is mostly a clockwise fence again, clockwise. So in each of these examples, what you're observing is that depending on how we end, if we end on a straightaway versus if we end on a corner, it may or may not be exact. But generally speaking, if you have a clockwise box, I've got a right turn, a right turn, a right turn, and then this is essentially a right turn, but we didn't actually turn right because we ended on the spot we stopped. So that wasn't getting counted initially. That's why we had 3 rights. But that's essentially 4 right turns with the last one missing. In this one we just did here, because we met on the middle area here, we had an extra right turn get counted up here. But if we had started here initially and gone over, then we would have ended there and we wouldn't have counted that as a right turn. That would have gotten missed, in which case it would be 7 and 4 instead of 8 and 4. So you do have to watch out about these numbers not being precisely exact. But for the most part, what it appears is if I have more rights, I've got a clockwise fence. And if I have more lefts, I have a counterclockwise fence. And again, depending on how you meet up, it should be more by either 3 or 4. So testing for an exact number, you would have to worry about that edge case on whether or not it met in the middle, or whether or not if it ends, then what was the first instruction, and would that have been a right turn or a left turn to include it? Let's look at a couple more really odd spots just to see if odd designs to see if we can verify that as being true. So if I go up here, I turn right, I'm gonna have right and left, and I'm just gonna make a wild fence here. I'm gonna go left, I'm gonna go right again, I'm gonna go left again, I'm gonna go left again, I'm gonna go straight and then straight, then I'm gonna go right, then I'm gonna go right again, I'm gonna go left, I'm gonna go left again, that's 5, I'm gonna go left again, 6, head down to the bottom, I'm gonna go left one more time, and then looks like I'm gonna run into the fence. Okay, if I do that, then I've got 5, 6, 7 lefts and 4 rights. Left is greater than 7 is greater than 4 by 3 total, which means I had 3 more turns to the left than I did to the right. And if we look at this, this generally appears to have been a counterclockwise fence. Let's do the original test case and test with this one. Okay, so we have this one. What we're going to want to do is to be able to identify, given 2 letters, whether or not this is a right turn or a left turn. So if I were to write this down, if I was going to say, what are all my right turns? What are all my left turns? And this is ultimately how you're going to want to approach this, is to probably build some sort of a library of these, or maybe just have a bunch of if statements that identify them directly. If I was going north, and then I suddenly went east, north and then east, that's a right turn, north, east. But if I was going north and then I went west, that would be a left turn, north, west. If I was going east and I suddenly went north, that would be a left turn. East to north is left turn. If I was going east and I suddenly went south, that would be right turn, east, south. If I was going, let me give myself one more room here. If I was going south, and then suddenly I turn to the east. So from south to east, that's a left turn, southeast. If I was going south and I went west, that is a right turn, southwest. Last 2. If I was going west and then suddenly went north, west north is a right turn, west north. And if I was going west and then suddenly went south, that would be a left turn. So west, south is a left turn. Okay, so now what we're going to do is we're going to run through and we're just going to count these up. Let's start with the simple case. So northeast is a right turn. East south is a right turn. Southwest is a right turn. We've got 3 right turns and no left turns. Right turns dominate, therefore this is clockwise. If it's right turns, it's clockwise. Just remember the clock's going around to the right like that. Let's do this next one. West south. West south is a left turn. South south is not a turn at all. South south south. Southeast is a left turn. East is straight. East-north, EN right here, is a left turn. Northwest, NW is a left turn. West-north is a right turn. Northeast is a right turn. East-east is straight. East-south is a right turn. South-south is going straight. South to east is a left turn again. East-north. East-north is a left turn. North, that's all going straight. North to west is a left turn. And then west is going straight. West to south is a left turn. All right, let's count these up. Left, I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 left turns. I have only 3 right turns. And again, that difference would be for the ending spot would have been a right turn, which is how that comes out. So all you need to do though is recognize that the left turns dominated. There were many more left turns than right turns. Because there were more left turns than right turns, this was mostly turning left, which means this is counterclockwise. All right, so as far as structures, data structures, again, you could have just a bunch of if statements with this. You could do if your character at I is equal to north and character at I plus 1 is equal to east or whatever. If you want to make a bunch of if statements, you could do something like that. That'll be totally fine and within the time complexity. If you're feeling a little fancier, you maybe want to use a set data structure. So you can check to see if the set contains a substring, or you can feed the 2 characters in. If you're feeling really fancy, you could make some sort of a table where you have north equal to 1, east, south, west, north, east, south, west, and you could put in like a +1 or a -1, and then say like, okay, northeast would be like northeast, whatever -1 means. A lot of ways you can oppose the structure, but ultimately the restriction is as you're going through, you can only look at any pair of letters one time. When you look that up, you have to convert that to a number or some sort of a counter where it's either north or where it's either right or left. If you want to have a counter and do +1 for every right turn and -1 for every left turn, you could just check if that's positive or negative. Or again, you could have a list and just be appending letter R's and letter L's. It'd be less efficient, but it would work just fine. However you want to do it. But ultimately, as long as you go through, when you find 2 letters that are not equal, you're able to look up whether or not that's a left turn or a right turn and keep track of that. And when you get to the end, just identify whether or not you had more left turns or more right turns. And if you had more left turns, then you've gone counterclockwise. If you have more right turns, then you've got clockwise. Best of luck, and I'll see you on the next video.